So, welcome everybody. What I wanted to give you first now is a very, very quick update of what we did on Monday. And then we are going to dive into topics which are relevant for the first exercise set. On Fridays, we will typically just use the first few minutes to guide you in the solutions of the exercises. And then you're going to use the rest of the day to use exercises. It means that we will also give you some reading assignments for the Friday session so that you are a little bit more prepared. And solving the exercises will then be something which is a little bit smoother. So the material I will cover today is very much related to what we are going to do in the first exercise, in particular the numerical part. But let me quickly remind you of some practicalities so that everybody is on the same level and that you can fetch all the material which you need for the course. And please never hesitate to ask questions if you have some. You've probably also seen that we have made a questionnaire, and we'd like to, because you guys have been confined now for 2 years almost. It means that you've lost perhaps one of the most beautiful things by being at the university, to get to know new people. So one of the things we did last year with a great success was to ask those of you who would like to team up with somebody else and haven't met so many people to actually sign up for the questionnaire and just say, I would like to collaborate with somebody. You can hand in the weekly exercises. We want you to hand them in individually, but you can collaborate 2 to 3 people. You just sign, you just write that I did work with this and this person. You hand in your individual stuff, but you can collaborate as a group. That means that this is something which is always very, very beneficial, because we tried to put together, last year we actually had some groups where people had never met each other. They'd all been confined at home. And we tried to mix people so that somebody was a wizard in programming, somebody liked more mathematics, somebody liked physics, and then somebody's like me, who is good at making coffee. The only thing last year that people like me were of no use because nobody could drink coffee together, right? Anyway, so we have different competences, different interests. So bringing people together is something which hopefully will bring back some of this experience of being at the university. So feel free to fill in that questionnaire, and then we will try to team you up with somebody. Sometimes the groups don't function, sometimes they do. We never know, right? But it's worth a try. And you can do things together. The group, obviously, you get the same grade if you have handed in the same solutions. But I hope you don't mind that. So this is very much up to you, right? Okay, so if we now look at the setup here, you have this website where we have basically all the material. And when you scroll down here, you will find our office hour schedule, the way we grade exercises. We have the deadlines. These are temporary deadlines, so we can always change them if something goes wrong or if there is a collision with other exams and so on. So we try to always accommodate your needs and wishes here. So, but the deadlines are more for your planning of the semester. If there is a conflict, please let us know. And we're also very, very flexible with deadlines. It doesn't mean that we put up a huge sign and says that we don't care about deadlines. So it's good to have a deadline, because you know that when you're done with it, you're done with it. And although I am a horrible procrastinator, and procrastination sometimes can lead to better insights because you keep thinking and thinking and thinking, it's, I guess you guys are packed with other courses as well. So to get things done, it's a good feeling, right? Okay. So you can find the textbooks. We have a PDF file of the main textbook. Many people like to buy it. It's a pretty good textbook, actually. It's one of the better around in the market. It doesn't have numerical exercises, but it has a lot of good text, and it gives you, when you read it, and actually, I recommend reading it. So don't be like my daughter, who says that reading is only something which old people do. I mean, we can just learn everything. We don't need to read manuals. My daughter always teases me for that. I mean, it's only people like you, Dad, who insist on reading a manual. Actually, that textbook is pretty nice. There's a companion textbook, which you also can download for free if you're on a university IP number. And else there is a version of the textbook here, and that contains a lot of numerical exercises. You will find every week a reading suggestion from these textbooks. And these kind of reading suggestions are linked up with the exercises and the stuff which we are going to cover. And then you will see that for every week, as soon as we're done with the lecture, we are going to upload the video. So this is I actually redid the video. And one thing we want to make is actually to add the transcript so that you can get the subtitles. That's a little bit more laborious, but we are planning to upload the transcript as well. So you can actually look at the transcript in case of hearing impairments, like me, for instance. I have a bad hearing, too much hard rock listening for many, many years. So the other thing I wanted to say is that if you scroll up here, you have the full textbook of the lecture notes, and then we have the weekly material. So let's dive into the weekly material here. And so this is this week's stuff, and you will see that there are some reading suggestions from Taylor's textbook, chapters 1, 2, and 1, 3. And every week you will see something similar. You will get an email where we tell you about what kind of things we would suggest to read. Now, if you look at these slides, there are lots of practicalities about Python, Python packages, and so forth. What we are going to do now is to dive into the last part of these slides, because this is a part which we need for solving the first exercise set, in particular the numerical part. So let's take a look at, so we're going to go through quite some pages. We looked at some of this on Monday. There is a repetition about vectors and quantities like cross products and so on. So we just put that for the sake of completeness, but we're not going to spend time in the lectures here because these are things which we're going to use, and most of you may have seen this before. So let's go to the stuff which is a little bit more interesting. And there is a lot of more material which we won't have the time to cover all every time, but this is also something we can use the exercises to do. What we are going to look at now is something which is very much linked up to the first exercise set, in particular the numerical one. So what we would like you for Friday, when we meet again, is to go through the material from that slide, which is slide number 54, till the end of the slides, because this is the material we're going to need when we are going to solve the exercises. So that's in addition to the textbook material of Taylor, chapters 1, 2, and 1, 3. We are now going to look at material which is linked up with the numerical solution, but also some of the basic topics. Now, again, as I said on Monday, don't be offended if we bring up a falling object. This is pretty boring, right? But we need this to bring up the common language and to get us started. So what we are going to look at now, we are just going to switch over to the whiteboard. So let's do that. So when it comes to the first types of exercises, the numerical exercise is an exercise where you have a data set, and that data set contains the position as a function of time of Usain Bolt's 100-meter world record in the Olympics in Beijing in 2008. So you're going to read in that one. You're going to calculate the average velocity, you're going to calculate the average acceleration. And one of the things you will see then when you plot the results is that Usain Bolt actually slowed down. So as an additional extra exercise, you could ask yourself, how fast would he have run if he hadn't slowed down? So that could be a kind of bonus exercise. But the thing you're going to do is actually to calculate these quantities based on a table. But we can actually produce that table. So let's look at the simplest possible case. So what we are going to do now is we assume that we actually know the position as a function of time for a falling object. And we're assuming that there is no friction, no air drag, no nothing. So we have a very simple formula, which most likely you've seen before. And I'm going to write this as a yt of 0. So I use this to introduce some notation as well. So minus 1/2 g times t squared. So t is time, g is the acceleration, the gravitational constant, the acceleration constant of gravity. So this is given by 9, the famous number, 9.8665 meters per second squared. So we are going to use that as units. And we are going to use this to catch many birds with a stone. So one is to introduce a notation which we're going to use. So we are going to define an initial time. And we define that as a t0. And often you would simply set that one to 0. That's a pretty common choice when you start solving the problem. So that would be your typical origin for time. So typically t0 is equal to 0 seconds. That's a pretty common choice, which we are going to use in many exercises. Then we are going to simplify the notation a little bit. So y of t0 is something which we will write as y0. So these are just notations which are going to need. Then we could define a time when this falling object comes to rest. So we could now say that there is a final time, t final, when this falling object, so this is a falling object in a gravitational field, so when y of t is equal to 0. That allows us to define a final time. So in the exercise which you have, you're not going to look at a falling object, but you're given numbers which correspond to Usain Bolt's world record. So that's measured for a certain time. I think it has something like 10 time steps. And then you have the position, and from that one you have to deduce velocity and acceleration. So you can define this final time when yt is 0. So if you do that, so yt, and we call it final, equal to 0, and then we have this y0, which could be set to 0. But let's just keep this as a given number, which we don't need to specify, minus 1/2 of g of t squared final. And then what we can do next then is simply to find this final time. So this t final, when we set it up again, you see easily that this is given by 2 times y0 divided by the acceleration of gravity here. So this is, I guess, this is not too complicated. And as I said, I hope you don't get offended if we are bringing up things which you have seen many, many years ago. Then, when we are going to solve things, we are going to define a domain where we want to solve for. So we would have time, which now would be defined between an initial time and a t final. So these are pretty common quantities which we need. Then, when we are going to solve things numerically, we will actually discretize. So if you look at the function which we have for y, you can perceive that as a continuous function. Now, when you look at data, data will always be discretized. So you won't have data as a continuous flow of time, but you will have some discrete measurements. So you will have a time 10 seconds, 20 seconds, 30 seconds, and so on. So real life is in a certain sense always discrete. So that means that when we are actually going to solve physics problems, we will either have data which we can collect. So you could actually run this experiment yourself by taking your cell phone. And your cell phone has an accelerometer. So you could take the elevator in a high building, and you could measure the acceleration as a function of time. You could download that one, and then you could integrate up, find the velocity you had, and integrate again, and find the height of the building. So that's actually a physics experiments you can do with your cell phone. The cell phone is pretty advanced, actually. I should rather say smartphone, not cell phone. Okay, so if you look at the discrete time, so we now let time go over to a discretized quantity. So there's going to be a T of I. And that's something you can think of as an observation. It means also that we are going to take a T of I, which now is given by some T0, which is the initial time. Then you're going to have an I multiplied with a time step. So this is normally called a time step. And this is to be defined. And I is now a set of measurements which we have. And I'm going to start with 0 because we started with time t0. There is another reason for why I start with time 0. If you think of Python, if you want to store this as an array, as a vector, Python array start by default with 0. So this means that it's very easy to map this over to a Python array when we are thinking in terms of computations. So this I goes from 0, 1, 2, up to a final number T of n, or n. So that means that my T final is going to be equal to a T of n. And I'm going to use this T of n to indicate my final time. Then you can define this delta t as your Tn minus the initial time divided by the number of integration points you have. So what you would typically would have then, if we're now looking at this one-dimensional system, so we would have time on the x-axis. So we have a t0, we have a t1, a t2, up to a tn. And then we have y here, which is the height we are looking after. In case of Usain Bolt's run, it's a distance he had at a given time for the 100 meter. So you would have a y0 here. There could be a y1 here. We could have a y2 here, etc. So a typical experiment which you're going to run, or when you run a numerical experiment, is that you will actually have something like this. So you will have a table of values. So in the first exercise, you are then going to have something like a table here. So you will have y and time. In this case, it's actually the position along the 100 meter. So you would have a y0, it's a t0, y1, t1, y2, t2, and so on, all the way up to t of n, up to, no, sorry, y of n and t of n here. So that's your array of data. So when you run a computations, this is exactly what you end up doing. Now, one of the things you can do then is that you can actually, with the positions you have, you can find the average velocity between two times. So if we define the average velocity between, and let's just say a time ti plus 1, which is the same as ti plus delta t. So we just move one time step, and t of I. Then we know that this velocity here is something which we can write. So I'm going to put a bar on top of it to indicate that this is an average velocity, because I take the average between two positions. So I'm just going to write it like a t here. So we can write it in a general way. It will be given by a t plus a delta t minus a y of t. And when we introduce a more discretized version, this is simply going to be given by a v bar of I, which we will indicate as a y, sorry, not that one. So it will be given by a y of I plus 1. We've moved one time step, minus y of I. So this is a more compact mathematical notation for the average velocity. So one of the things you're going to do in the first numerical exercise is to read in that table and simply look at the velocity, the average velocity between two observations. And then one of the things you will see is that as you move close to the end of the race, you will see that the velocity actually drops. And if you watch the video, you will see that Usain Bolt actually slows down in the last 10, 15 meters. Okay, now the thing which we are used to see is something which we would call the instantaneous velocity. And we know that that velocity is actually given by, so v of t as a d of y dt, and that's given by the lim of delta t goes to 0. And then I would have a y of t plus delta t minus y of t divided by delta t here. So in real life, we never have a continuous quantity. We have discrete observations. But when we set it up mathematically, we now assume that the velocity is given by a continuous function. That's an assumption we make. So you can then define what we normally would call an instantaneous velocity. But keep in mind that when you do things numerically, when we're going to solve things, the equation which we will be looking at is an equation like this. This is actually the equation we will try to compute. We can do the same with the acceleration. So if you take the acceleration then, so a of t, and this is another ingredient you need for the exercise. So the acceleration is defined as the derivative of the velocity. So this is again, when I don't put a bar on top of it, this means the instantaneous velocity, or the assumption we made that the velocity is a continuous variable. Then we know that this quantity here is then given by simply lim of delta t goes to 0. But now I would have the velocity at t plus delta t minus v of t divided by delta t. And that's the quantity which you will need to set up when you're going to solve this numerical exercise, because you're being asked about what is the acceleration. And you will see that Usain Bolt accelerates in the beginning, and then when he's slowing down, the acceleration becomes negative, right? That's a typical sign that you're slowing down. So these are the typical quantities which you're going to solve numerically when you're going to look at the first exercise. The kind of program you're going to write for the first exercise is something which we will build upon when we move to the next exercises, and so on and so on. So one thing which I wanted to bring up now is the connection between, so we just assumed now that this quantity here, the position in the y direction, has this mathematical formula, but we didn't prove it. So we can show this from the equations of motion. Now, our law of motion is Newton's law. So that means that in our case, what we are going to have is something which is given by the force, and then we have the mass of the object, and then we have the acceleration, which is a function of time. In general, the acceleration is a function of position, velocity, and time. So we should actually write this. So if we now divide by m, this is in principle a quantity which depends on position. And we are just now looking at the case in one dimension, okay? So it has should be a function of velocity and time. Sometimes the force, if you think of the gravitational force, that is a force which is time independent. That has some very interesting consequences for us because it leads to conservation of energy. I'm just anticipating something which is coming a little bit later. So this is the general dependence of the acceleration. So we would typically rewrite this in terms of A over dy, dt, and t, like this. Now, the assumption we are going to make now is a very simple one. So we know that the acceleration is actually given by dv dt, right? So what I could do now is simply to integrate up this equation. So I could start at the initial time and integrate up to a final time. And then I would now assume that they have some initial conditions. And the assumption which I'm going to make with the initial conditions is that my v at time 0 is equal to this quantity v0, and it's equal to 0. So that's just an assumption I'm making now, just to make life a little bit simpler. And then I'm also going to set t0 equal to 0 seconds. So 0 meters per second and 0 seconds. So these are my initial values. Now, when you're solving this type of equations, you do have an infinity of solutions because you have an infinity of initial conditions, right? So you can place yourself at 1 meter, 10 meters, 50 meters. So you have an infinity of ways of organizing your problem. But when you have specified the initial conditions, there is a unique solution if you can solve the equations and if the solution exists. So you can now integrate up. So I would now integrate d of t from 0 up to time t, and then I would have my acceleration, t prime, and that should give me my velocity. So this would actually give me v of t minus v0 when I integrate up. So what I could do now is to assume that the acceleration is simply given by minus g. So I'm assuming that there is no air drag, no nothing. It's just simply an object falling in a gravitational field. There's no air resistance, no nothing. And you know that we can integrate this up now. So if we put this one to 0, that means that what I'm doing now is to integrate up from t of minus g times dt prime. And this is equal to v, the final time, minus v0, which I put to 0. So we actually decided that that one is 0. So the object is at rest when we begin. And that means that what I get then is that v of t is actually equal to minus g times time. Then we know that v is actually equal to dy dt, right? So in the exercise, you're given the positions and as a function of time. But you could start the other way. You could start with the forces acting on the system, and then you could find the equation for the displacement. So you see the difference? So you can perform an experiment and measure, for instance, the height of a building or measure the position of Usain Bolt as a function of time. Then you can extract velocities, accelerations, or you could start with the forces. If you know the forces, then you can integrate up the acceleration. You find the velocity, you integrate up again, and then you find the position. So when we are doing things numerically, it's essentially this kind of approach which we are going to do. And as you will see, when you do things numerically, if you write a general program for solving the differential equations, the only thing you will need is to change the acceleration. and then you can move to a new physics case. So the basic numerical solver is a solver which you will use again and again and again. But you are going to plug in the physics, and the physics is given by the forces and the initial conditions. And that's where you have to do the thinking, where you have to develop the insight about the physics of the system. But the kind of framework, the numerical framework, is actually going to be pretty the same. The only thing you need to change actually the forces, and the equations are going to be very much the same, as you will see later on here. So I need to check time here because I have a bad tendency to just talk and talk and talk. We take small questions. Is this okay? Too fast? Too slow? I tend to be a little bit slow, right? Okay. Any questions about what we've been saying? Yeah. Say it again.
What are the tick marks on the T's that you have up there?
Yeah, so this is just so the T prime is just to indicate that that's another variable than the final time. So if you look at the quantity which we have here, so let's just so what I did here I just indicate that this is not the same time as the final time. This T prime is just an integration variable. It's a dummy variable. So I could actually have used another name for it, but now I just call it T prime to distinguish it from the final time, because the final time is a value which you choose, whereas the T prime is an integration variable. Okay, so let's continue. More questions, guys. So both George and Julie will try to answer you on the chat, because it's or you guys online, because it's a little bit more difficult for me paying attention to the people here and then online. So Julie and George are actually answering on the chat here, and they're fantastic, by the way. Okay, so let's switch a little bit and look at how we can program this. So let's take a look at some of the basic steps in setting up a program which takes in the data and plots the data. So let's switch a little bit to the Jupyter notebook. Well, that should be here. So one of the things which I have done is actually to, I like to make some kind of common things first. So if you look at what you have here, I like to save figures to a folder. That's always useful because you made a run, and then you can save the run in a folder. So this is just a kind of background thing in Python, where you can read data from file, you can define a folder, you can have data you need to read, or you write out figures and so on. So this is just some kind of handy background. But the thing which is interesting for us now is actually the first part of the program here. So what I'm doing now is to define G, as you can see here, and then I define the initial position. So that is the Y0, which I had in the notes, okay? Now, the next thing which I do now is to define my delta t. So this is one way of doing it. When I have defined a delta t, I can then set up an array for time. So this is done here, as you can see. So if you look at this one, I use the A range. So it starts at 0, my initial time, and it has a final time. And then when I give delta t, it finds out how many steps I should have. The alternative here is that I define the number of integration points. So what I could do then, if you now look at what we have here, so I could go up and I could simply say, I define rather the number of integration points, n, suppose that's given 100. Then I would define a final time here by using that formula which we looked up in the notes when we defined the final time for the falling object. Then I could now say that my delta t, this quantity delta t here, is equal to t final, and the t initial is just 0, divided by n. So when I have done that, what I could do next is to define an array which contains all the times using that formula. So I would have to make a loop then. So I could then say that t of I need to make a loop actually to do that, is equal to t0 plus this I times delta t. Like this. I would have to have a loop which runs over all the t values and sets up an array which contains all my times. So there are two ways of doing that. And you will see this last recipe, you will see that at the bottom of this Jupyter notebook. So the first one is just to define delta t yourself, and then use the A range, and then define from 0 to t final, and then it sets up all the t values in between. Are you familiar? Is everybody familiar with the A range function? Excellent. Good. So feel free to use these programs when you're doing the exercises. I've put all this material out here to help you. Don't feel like that you should write everything from scratch. If you see something which functions, use it. Because what we're actually looking after is to develop your insights about physics. So let me just take away some of this because we don't need it. Now I'm setting up the array of times, and then I'm setting up the y, and then I produce a table. And I like to use pandas, this data frame. It's a package in Python, which is very popular for handling arrays and so on. Feel free to take a look at it. You don't need to do that, but you could simply just produce it. And you see now what I'm doing. So at time t equals 0, we are at the height of 10 meters. And then we go down, down, down. And after 15 or 16 time steps, we are down to 0. So I'm just plotting the last time step where y is not 0. So this is the typical plot which you would make. The way we are setting up things here is pretty close to the way we are going to solve the first numerical exercise. Except that then you will actually have to read in the data. The data is given to you in terms of a table of x and time. So then the next thing which we discussed are these average quantities. So you could define now the average velocity and set that up. And then you would typically continue. So you can define, these are just notations which we defined also in the on the whiteboard. We can then have a more compact notation. This will be the instantaneous velocity. And then we can define the instantaneous acceleration. So we went through the derivation of these equations on the whiteboard. So they are just collected here for the sake of completeness. So then the thing which I wanted to say a little bit about is the other way of solving this problem. So let's go back to the whiteboard now for the last minutes which we have at our disposal. So let's stop here. And then we go back to the whiteboard. So if you look at what we did here, we took, so one thing is that we can start with a fundamental law. This is Newton's law. So we have an expression for the acceleration. And if we are lucky, we can integrate and get a nice analytical expression for the velocity. And you know that when we have this one, we can now go back because we know that velocity or the position velocity is now given by v of t is given by dy dt. So we can integrate up the dy dt. We know the expression for the velocity. So if we integrate up again, what we would get now, so we integrate again over time. So we would then have an integral which goes from 0 up to a given time. And now we have a dt prime multiplied with v of t prime. And we know the expression for that one because that is simply minus g times t prime. And this is now equal to y of t minus this y0, which is our initial position. And the integral which we have is pretty simple to do. So if we now put t0 equal to 0, what we know then is that this simply becomes, when we integrate up, I get y of t is equal to y of 0. I just shuffle that over to the other side, minus 1/2 of g times t squared. So what I could do now is, since this is a case where I know the acceleration, I was very lucky because I could integrate up. So what you could say now is this is what we would call approach number 1. So this is approach 1. And then there is a wisdom 1, which we can extract here. If you can integrate, do it. So typically, if you have a simple term for the force, then you can divide by the mass, you integrate up, you find the velocity, and then you find the acceleration and the position. If you can integrate and get an analytical answer, if you can integrate, do it. So this sounds a little bit like a pretty, how to say, a not very advanced statement. It's like, why should we do physics when, if this is the kind of wisdom we are getting? The problem is that it's not in all cases when we can integrate and get a nice analytical solution. But integrating up the equations is essentially what we end up doing. But what we could take now is approach number 2, where we actually solve these equations as differential equations. So you have one approach, the integration approach. And if that works, you should use it. But the other approach, the other standard approach, is actually to solve differential equations. So sometimes you can solve the differential equations analytically, but in most cases you have to do it numerically. And you will see in one of the exercises which is coming, that if you add a air resistance to this simple falling object in 2 dimensions, you will actually end up with an equation which you cannot solve analytically to get a nice closed form expression for it. You can actually only solve it numerically. And that's actually most of the cases you do in science. You have to revert to some numerical simulations. So this course here is going to try to keep a balance between doing things with paper and pencil, but also doing things numerically. And when you do things numerically, that's where you actually can deepen your insights about physics problems. So if you want to study the solar system, you can't find an analytical solution for all the planets. You actually have to study it numerically. And when you have a program which simulates the solar system, you can actually ask yourself, what if I change the gravitational force? Instead of 1 over r squared, what if the gravitational force was 1 over r cubed? Would the solar system be stable? And then you could try it. So that is the way you will combine the different tools. So doing science means actually solving scientific problems with all available tools. And there's nothing to be ashamed of if you can't find an analytical solution, because in many cases they don't exist or it's impossible to find them. But that doesn't mean that you cannot solve the problem. When you do a numerical approximation, you also have to keep in mind that numerical approximations will have mathematical errors with them. So we have to be aware of the type of errors which you can make. So I hope you can see this kind of different things, because this is what defines you as a scientist. And you as physicists or people who are going to do natural science or science in general, you're also the people who are going to develop the next insights, the next software, and so on. And that means that we have to have an understanding of what is going on. Okay, so that was a little bit enough preaching. So let me take the approach number 2, since we announced that one. This is going to be a little bit more the topic next week, because on Friday, we are going more to look at solving exercises. But the approach 2 means that we solve the equation of motion, which in our case is Newton's law, as a set of differential equations. So you can call approach 2 solving differential equations. So what does that mean? If you look at Newton's law in its simplest form, if we now have just one object with a given mass, and it's under the influence of an acceleration, we know that this is the same as m times dv times dt, which is again the same as m times the second derivative, and we're still in one dimension. Actually, I thrive in one dimension. Life is scary when I move into 2 dimensions and 3 dimensions. And again, according to my wife and my daughter, I'm a typical one-dimensional person. So I thrive in one dimension. My wife and my daughter, they always agree. I don't know why. Okay, that joke's apart. What you can do now is to, this is a second order differential equation. You would define initial conditions. Initial conditions, you need to define that, because else you will have an infinity of solutions, but you want one specific. So you would define an initial velocity, v0, you would define an initial position, y0, and you would define a t0. So this defines the start of your system. Then the thing, since this is a second order differential equations, in some cases, you can solve it analytically. And we will see that. You've probably seen the harmonic oscillations, right? If you have a block which slides back and forth, that is an equation you can solve analytically. But the standard approach is typically to split this into 2 first order differential equations. So that means that you would have 2 equations, and these are the ones which we are going to deal with numerically next week. So these 2 equations, there's going to be one for the velocity, which is given by the derivative of dy dt. So first order differential equations are much easier to solve analytically, paper and pencil, and numerically. And then there's the other equation, which is a of t, which is given by dv dt. And the thing which we will have is an analytical expression in most cases for the acceleration. So if you look at the equation which I have here, this one, this is normally given by Newton's law. So if you have a gravitational force, you have an expression for the forces and the acceleration. If you're looking at a sliding block, you know what the force is. So essentially what you will have to do when you set up a solver for the problem is to identify the forces. And that is where you have to bring in your physics insight. So finding the forces gives you the acceleration. And when you have spelled out the forces, then you can start solving the problem. So mechanics, this course here is actually about the time evolution of objects under the influence of Newton's law. And Newton's law is our equation of motion in this course here. And we are just going to look at different permutations of accelerations. So the thing when you have a nice solver is that you simply have to think, what is the physics of this problem? which are the forces which are acting on our system. And when you've done that analysis, then we start solving. So we're going to stop here now. So I'm just going to leave you guys in a kind of suspension, waiting for the next episode of this season. So that next week we are going to look at how we actually solve this type of equations. Now, feel free to ask questions. Things are unclear. The video will be uploaded after the lecture. Same with the handwritten notes here. You will find them online. I'm going to revisit the video and see if it is okay, because on Monday it was not okay. Okay, I'm going to stop the recording here.